I am Dr. Ruma, Assistant Professor of the HIT, Haldia Institute of Technology, Haldia. Today I am going to present laser and what is the characteristics of laser, working principle of laser and the application of laser. So first we need to know what is the full form of laser. The full form of laser is light amplification by stimulated emission of radiation. So it's very simple that light will be amplified. How? By stimulated emission of radiation. So now we need to know what is stimulated emission. As per our knowledge, we know the absorption and emission. So what is the absorption? This is the lower energy state E1 and the higher excited state E2. So when the incident light is falling on the lower excited state atom or the ground state atom, then it will absorb the radiation and then the atom will go to the higher excited state. This is called the absorption, which has been shown with this. And the emission process. Emission means that there are higher excited state, there are few atoms and they will come to the ground state by emitting some radiation. That called the emission. But there are two types of emission. In the normal case, there are atom at the excited state E2. When it is coming to the ground state, it is giving the radiation and it is called spontaneous emission. Then what is stimulated emission? The stimulated emission is little bit different from the spontaneous emission. For the case of spontaneous emission, the atom which are at the excited state, they will just come to the lower excited state and we will get some radiation. But for the case of stimulated emission, the state-wise it has been represented. First thing is that there are atoms at the higher excited state. With the same energy of the photon, that means with the energy E2 minus E1, the atom will come to the with the same energy photon, they will come to the excited state and they will interact with the excited state atom and then we will get two emitted photons with the same energy. Here if we see the schematic, that this is the excited state atom and the same energy radiation is coming and it is interacting with this excited state. And then what will happen after this interaction? There will be two photons with same energy. This is called the stimulated emission. So what is the difference between stimulated emission and spontaneous emission? Stimulated emission is that you need the external excitation to the excited state atom. But for the case of spontaneous emission, you don't need any external excited state, external excitation. What are the property of the stimulated emission of radiation? This is the radiation with energy H2 and obviously we can see from the schematic there will be two photons with same energy. First thing is that they will be highly directional. It means that here the incident photon is falling in this direction and the emitted photon is also emitting in the same direction. They will not come in this direction. No photon will come in this direction. they will only follow this direction. That is called the highly direction. And the thing is, these two photons, they will be coherent. That means they have constant phase difference. It is not that they have same phase. They have constant phase difference. Now the characteristics of the laser. What are the characteristics of laser? First is they are highly monochromatic. Second is high degree of coherence. From the last slide, we have seen that they are highly directional also, and their brightness will be very high. These are the characteristics property of the laser. Now the thing is, what is the meaning of high monochromaticity or highly monochromatic? Here, this is the radiation which is coming out as a form of laser, and if we measure it, then we will get a graph in terms of the wavelength and intensity. And this is called the full width half maximum. For the case of monochromatic light, this full width half maximum, this value, it will be close to 0. Ideally, it is possible, but in real life, it is not possible, but it will be as small as possible. So there is a estimation that for the case of laser beam, this delta lambda, it's 0.001 nanometer, whereas for the case of normal light or sunlight, this delta lambda is 300 nanometer. So from this thing, we can get an idea that laser beam is highly monochromatic as compared to the normal sunlight. Now, the thing is, we know that what is laser, what is the characteristics of laser, but now the question is how you will prepare the laser signal. For that thing, we need to know the working principle of laser. So there are three main components if we want to make the laser signal. One is active medium, second is pumping source, and third is optical result. One by one I will discuss. First is active medium. So what is active medium? So active medium is basically the collection of atom or molecule or ion, or they can be the mixed of them in the gaseous state, liquid state or solid state. This is called the active medium. For example, this is a box. Inside this box, there are some ion, molecule or atom, whatever it is, or their mixture. This is called the active medium in the simple. Now the thing is, in the active medium, you will give the external excitation to generate the laser signal, because to generate the laser signal you need the stimulated emission, and you have to give the external excitation. So when you will give the excitation, there may happen the stimulated emission or may happen the spontaneous emission, which is not in our hand. So because of that thing, first you need to know, when you are giving the excitation from outside in the active medium, which is the most probable? The stimulated emission or spontaneous emission? So let's see that part. To determine that thing, first we need to know some calculation, that Einstein AB coefficient, that will help us to determine that is the higher, the stimulated emission or spontaneous emission. So for that calculation, there is one schematic diagram. This U1, which is the lower excited state or the ground state, and this E2 is the higher excited state. And their energy difference E2 minus U1 is H2. So this arrow is showing the absorption and this is showing the emission. So here this N1 is the number of atoms per unit volume at any instant of time t. Here the number of atoms, if I draw it here, so the number of atoms per unit volume is N1 and number of atoms at the excited state per unit volume is N2. And this is the incident radiation, which is the function of U. So this is the energy density. That means the energy incident per unit volume. So the rate of absorption is proportional to N1 and U. The absorption of the atom, that is proportional to N1 and U. How? That if there are more number of atoms present, then more number of atoms can go to the higher excited state. That means the rate of absorption is proportional to N1. Another thing is that there are more number of atoms, but the density of the incident light is less. Then only few number of atoms can go to the higher excited state. If you increase the energy density, then more number of atoms can go to the higher excited state. So the rate of the absorption is not only proportional to N1, it is also proportional to U. And the rate of the absorption per unit volume, per unit time is this one, where B12 is the proportionality constant. That means the rate of absorption per unit time per unit volume is proportional to N1 unit. And if I want to remove this proportional sign, then I need one proportionality constant, and which is B1. B12. Now this is the number of the absorption per unit volume per unit time is this. Now we also need to find out the number of atoms for the spontaneous emission and for the stimulated emission. For the case of spontaneous emission, it's depend on the number of the atoms which are at the excited state. If I again draw it, this is N2 and this is N1. So how many number of atoms are there that will give you the idea that how many number of the radiation you will get. If you increase the number of the atom at the excited state, then you will get higher number of emission. But it does not depend on that how many radiation is falling on that, because it's only concerned about that how many number of the atom at the excited state. So it only depends on the number of the atom at the excited state. So that's why the number of the emission, spontaneous emission per unit volume per unit time is into A21, where A21 is the proportionality constant. Now, for the case of stimulated emission, we need the external excitation to the excited state. That means we also need to consider the UNI, because we need the same energy E2 minus U1 that will interact with the excited state atom for the case of stimulated emission. So it is proportional to the number of the atom at the excited state as well as UNI. That's why this one. And the proportionality and the stimulated emission will be given by N2 B21 UNI, where B21 is the proportionality constant. And this proportionality constant, they are called Einstein AB coefficient. But our aim is to find out that what probability is the higher, stimulated or spontaneous in the active medium. So for that purpose, at thermal equilibrium, the number of the rate of the absorption and the rate of the emission, that must be equal. That's why we have written down this equation. This equal to, this is the absorption. As many number of the atom is going to the higher excited state, that many number of the atom will come to the lower excited state. And this is the due to the spontaneous emission and due to the stimulated emission. And from this equation, we have find out the value of UNI. The thing is, N1 by N2, this can be written as e to the power E2 minus U1 by kT. And E2 minus U1 is h nu. So N1 by N2 is equal to e to the power h nu by kT according to the Maxwell-Boltzmann statistics. So if we use this thing here in this place, we can write it down like that. And here I have modified this, just divided by B21 everywhere. B21 and B21. So we will get this equation number 1. So after that, so this U is also this energy density. We also get one expression according to the Planck's law in the quantum mechanics, and according to this formula, this equation 2 we get. If we compare equation 1 and equation 2, here I have also written down equation 1. So if I compare equation 1 and equation 2, we will get the value of the Einstein AB coefficient. And here we have seen that B12 and B12 equal to B21. If just compare this thing, here the coefficient is 1, that is equal to 1, and the rest of the part, this is same as this one, this is same as this one. So this will be equal to this one, this constant value. This will be equal to this constant value. So we got this. From this thing, we can also write down this one using the help of equation 1. And what is this A21? A21 is the A21 divided by B21 U. A21 is corresponding to the AV coefficient of the spontaneous emission, and B21 union is associated with the stimulated emission. So if I find it out, the ratio, so we will get a comparison or the ratio between the spontaneous emission and stimulated emission. So for the normal optical source at temperature 1000 Kelvin with wavelength 600 nanometer, this value is 10 to the power 10. So with this value we can see that the spontaneous emission is very high as compared to the stimulated emission with the normal optical source. So it's conclude that in the normal situation, in the active medium, if we give the excitation, we will get only the higher probability of the spontaneous emission. So that means we will not get the laser signal. Then how we will get the laser signal? For that purpose, we need one solution, and which is called the population inversion. So this is the normal situation. This is the normal situation, that at the normal temperature, the higher number of the atom will be lower excited state and the lower number of atom will be at the higher excited state. And it follows the Maxwell-Boltzmann statistics. But if we want to get the laser signal, we need the stimulated emission. And because of that, we need this. That means at the normal temperature, we have to get this situation, that higher number of the atom will be at the higher excited state and lower number of the atom will be at the lower excited state, which is called the population inversion. And in the next class, I will discuss how you will get the population inversion.